Welcome on the day 10 of this online course Physics with Scilab. Today we will see the solutions of Schrodinger wave equations for some basic quantum mechanical system. First we take the example of particle in infinite square well potential. Here the particle will have zero potential energy inside the well and infinity outside. Therefore, the wave function is discontinuous outside of well, that is psi of x is 0 for x is less than or equal to 0 and x is greater than or equal to 1. Then the Schrodinger equation for the particle in the well may be written as d2 psi by dx square plus 2m upon h cross square e psi equal to 0, or d2 psi by dx square equal to minus 2m upon h cross square e psi. The boundary conditions are psi of x is 0 at x is equal to 0 and at x is equal to 1. We take d psi by dx is equal to 1 for simplicity, since it is a slope of psi at the boundaries, therefore it just decides the scale of the figure. Here we consider the particle to be an electron, for which we have mc square is equal to 0.511 into 10 to the power 6 electron volt, and the constant h cross c is equal to 1973 electron volt angstrom. To write in Scilab, I use notation U for psi, then I use the symbols T1 and T2 for U and du by dx, which will lead to these two first order linear differential equation which we have to solve in Scilab. So let's move into Scilab. So here is the code written to solve the Schrodinger equation for the particle in infinite square well. CLC and CLF commands for clearing the console and graphics window before execution of program. Then function du is equal to f of x t e. Here du1 and du2 are the two first order linear differential equations obtained from our original second order differential equation. X in the argument of the function f is the variable in wave function. T is the new notation used for the wave function, and E is the energy of the particle. Here we have to supply the value of energy for a function. Then variable x is from x is equal to 0 to 1 with increment of 0.01. The solution of Schrodinger equation U is given by the function ODE. The first argument is the initial conditions, that is u0 and u0 prime at x0, then the variable x, and then list function includes e in the function f as a variable. The command display for displaying the values of a function, and command plot 2D for plotting the wave function. First I am using the value for energy E is equal to 10. Then save and execute this program. So these are the values for the wave function for different values of x, and this is the plot for the wave function against the x. So E is equal to 10 is not the eigenvalue of energy, because it is not satisfying the boundary condition that wave function should be 0 at the boundaries. The wave function is not 0 at 1 but has the positive value for t is equal to 10. Now I am using e is equal to 50. Save and execute. This time wave function has negative value at x is equal to 1 for e is equal to 50. So e is equal to 50 is not energy eigenvalue. Since our wave function is positive for e is equal to 30 and negative for e is equal to 50, therefore the energy eigenvalue must be in between 10 and 50. So I use the average of 10 and 50 as a new input for energy. So average for 10 and 50 is 30. Save and execute. Again, wave function has a positive value at x is equal to 1 for e is equal to 30. Now the wave function is positive for e is equal to 30 and negative for e is equal to 50. Therefore, the energy eigenvalue must be now in between 30 and 50. So now I will use the average of 30 and 50 for E. So average of 30 and 50 is 40. Save and execute. So this is now the wave function. Again, at x is equal to 1, the wave function has negative value. So E is equal to 40 is also not an energy eigenvalue. Since wave function is positive for E is equal to 30 and negative for E is equal to 40, therefore the energy eigenvalue must be in between 30 and 40. So I use the average of 30 and 40, that is 35. Then save and execute. Again I get the value of the wave function at x is equal to 1 positive. Therefore the energy eigenvalue must be now in between 40 and 35. So now I will take the average of 35 and 40, that is 37.5. Save and execute. So finally at 37.5 I get the value of wave function near to 0 at x is equal to 1. So to get more precision in the value, I need to repeat these steps hundreds of times. Though it is easy, but it will take time. So can we repeat these steps in the program itself so that we can get the result in seconds? Yes, we can do just by adding some more lines in the program. Here is the modified program for getting the eigenvalues and eigenfunctions for the particle in infinite square well or a one-dimensional box. The function is same as we have discussed earlier. The only change I have made here is that in this I have gave two inputs of energies E1 and E2 at a time through this input function. Then the initial conditions x0 is 0, u0 is 0, u0 prime is 1, it's same as before. The values of x are from 0 to 1 with the increment of 0.01 is also same. But here E1 and E2 are the values of energies for which the wave functions U1 and U2 are to be computed. Now, if U1 have a positive value at x is equal to 1 and U2 have a negative value at x is equal to 1, then average of E1 and E2 will be taken, for which again the wave function U3 is obtained. Now, if U3 is negative at x is equal to 1, then the product of U1 at x is equal to 1 and U3 at x is equal to 1 is less than 0 or negative, because the U1 function has the positive value at x is equal to 1 and U3 function has a negative value. Then we replace E2 by E3, otherwise E1 by E3, for which I have used if-else statement in this program. In the if-else statement, in the argument U1 of 1 comma 1001 means the 1001th value of U1, which is corresponds to x is equal to 1. Similarly here U3 of 1 comma 1001, so here is also the value of U3 corresponding to x is equal to 1. If this product is less than 0, then use U2 is equal to E3, else E1 is equal to E3. So this if else statement will end here. Then display energy eigenvalue E3 and then command X plot the U3 against X. So I will save and execute this program first. So I gave input 10 for E1, enter. Input for E2 is suppose 50. So now this is the energy eigenvalue and this is the plot for the wave function. But you can see this is not 0 at 1. So this is not the appropriate energy eigenvalue. So I need to repeat these steps hundreds of times. So for this, I'm using the for loop in this program to repeat these steps for 100 times. So syntax for loop is for I is equal to 1 to 100, for repeating these steps for 100 times, and then end. So these are the steps I want to repeat 100 times. So I will put these steps into this for loop. So now this is the modified program with the for loop. So now I will save and execute. So it is asking for first value of the energy. Suppose I give 10. Second value of energy is suppose 50. So now this is the energy eigenvalue 37.592657, and this is the eigen function plotted against x, and you can see at x is equal to 1 the wave function is 0. That means this is the energy eigenvalue for the particle in one dimensional box or infinite square well. So we will try for next energy eigenvalues. So again I will save and execute this program. Now first energy guess I will give 100 and second is 200. So the second energy eigenvalue is 150.37, and this is the wave function for a particle. You can verify these values of energy eigenvalues and eigenfunctions from the standard formula. Again, I will save and execute this program for one more range, suppose 200, and so this is the next energy eigenvalue and the eigenfunction. Now I will give 500 and 700 and so on. In this way, we can obtain different energy eigenvalues and eigenfunctions using this program in Scilab for the particle in infinite square well or in one-dimensional box.